Welcome back to Chapter 3, where we are looking at more derivatives. In this section, we're going to be looking at implicit differentiation. This is a method of differentiation that is very, very useful. It comes in handy for a lot of things. For example, the next couple sections, we're going to be looking at inverse trig functions and logarithmic functions, which we can find the derivatives of both of those implicitly. Now, the way I look at implicit differentiation is it's just the normal differentiation, except we're not skipping a couple steps. And I'll explain that when we get there. But basically, like every time I'm finding the derivative, I'm actually doing it implicitly in my head. So we're going to see what this is. Oh, and so we'll get there. Learning targets. So find the first and second derivatives using implicit differentiation. Find slopes of curves using implicit differentiation. Find where slopes of implicitly defined curves are defined. Find equations of lines, tangents, or normal curves. Find equations of lines tangent or normal to curves using implicit differentiation. And then find derivatives of functions with rational powers using the power rule. That last one is super easy that we've actually already talked about a little bit. So, implicit differentiation. This we use to find implicitly defined functions. Well, what is that? Well, an explicitly defined function is something like y equals x squared plus 3x minus 7. It's y equals something. So functions are explicitly defined, generally speaking. And we can find the derivative of this. I'm going to use the dy over dx notation. It equals 2x plus 3 from the power rule. That's all that is, that's what the derivative is. I left some space there because I'm going to show you the steps that we actually skipped in the process, which is implicit. So that's an explicitly defined function where we can just do it this way. An implicitly defined equation would be something like this. Now, I might accidentally call them functions just out of habit. A lot of times these are not actually functions. For instance, this guy, this x cubed plus y cubed minus 9xy equals 0, looks kind of like that. Actually, it looks exactly like that. And so since we have these vertical lines here, it does not pass the vertical line test. It is not a function. It is called a foliot. Yes, this is called a foliot. This specific type of graph. So, how are we going to find the derivative of this? Well, for this, we have to use implicit differentiation. We're not going to start out with this one, though. We're going to start out with something a little bit easier. But first, let's look back at this equation that we had so we can see what implicit differentiation is. So, with the derivative here, we have the dy over dx. That's the derivative of y with respect to x. Now, when we're doing this, we can find each variable separately is going to have its own derivative. For example, the derivative of y is just dy, right? That stands for the derivative of y. Then it equals x squared. Well, that's going to be 2x times the derivative of x. That's a little bit of chain rule going on there. All right, plus 3x would be plus 3 times the derivative of x, and then minus 7, that's a constant. And so then what we do is we're going to get all the dy's on one side of the equation, all the dx's on the other side of the equation, factor out, and then divide so we have dy over dx equals something. So we have dy equals, we can factor out the dx, so we have 2x plus 3 dx, and then we divide by dx to get back to this equation. That's one way of doing implicit differentiation. Another way, which is perfectly fine. I don't do it this way because I find people, they tend to make mistakes, is when you see the y, you put a dy over dx or a y prime. So anytime you take a derivative of y, and then the x's don't get anything. I like doing it this way because every variable should have a dy or a dx following it. So we will get back to our foliate later. But first, let's do one that's a little bit easier. Let's do the sideways parabola. This has a graph of y squared equals x. Now, yes, we could make it y equals the square root of x, except we don't know how to take the derivative of a square root yet, unless, of course, we use a definition. But we don't want to do that. We'll get to that later on in this lesson. So we're going to do it implicitly. So implicitly, we have y squared. What's the derivative of something squared? We have 2 times the something times the derivative of the something equals x. What's the derivative of x? Dx. I know it's 1 dx. Again, usually the shorthand, we already have that factored out and divided over. Now we want to divide because we want dy over dx equals something. So we can divide by the dx, and we can divide by the 2y to get dy over dx equals 1 over 2y. So that is the derivative found implicitly. Sometimes it's possible to solve for y, like y equals plus or minus the square root of x. So we could make it 1 over 2 times plus or minus the square root of x. Like we could substitute that in, but it's not always possible to solve for y, like with the equation that we saw on the other page. We can find the derivative at a given point. Now, this isn't when x equals something, because here there are a couple values when x equals something. So we have to actually pick a specific point, like the point 4, 2. We could find the derivative at the point 4, 2. Now, first thing we want to do is check to make sure 4, 2 is actually a point on the graph. Yes, it is. You don't want to take the derivative, like say 5, 5, because that's not on the graph. It doesn't actually have meaning. Could we plug in 5, 5 into our equation, our derivative equation, get a value? Yes, you could. But again, it has no meaning because the graph isn't there. So we can do it at 4, 2. So we can plug in dy over dx equals 1 over 2 times y, which in this case would be 2, to get 1/4. So the slope of the tangent at 4, 2 is about 1/4. Well, it is 1/4. It's not about 1/4. It is 1/4. We can figure out where I'm trying to think of how the study guide or how the learning target did it. Slopes of curves, slopes implicitly defined, or where they are defined. So where is this curve defined, or where is the slope of this curve defined? So it's defined everywhere except when it's vertical, because the slope is undefined at that time. So what would make this vertical? The same rules apply as when we're finding the domain, except we might not just be looking for x. In this case, we have 1 over 2y. So this 2y can't equal 0, which means y can't equal 0. So it's defined everywhere. Well, and also looking at it, y has to be positive, or x has to be positive, because y squared will be positive, so x will be positive. So it's defined when y does not equal 0 and when x is greater than or equal to 0 is when that slope will be defined. Otherwise, we can't get a point, or when y equals 0, we can't actually have a slope there. So we saw the implicit differentiation. After that, it was just finding the slope. We could find the tangent line. We have a slope. We have a point. You can find a tangent line. You can find a normal line by using -4 for the slope because it's perpendicular. We'll actually see that in a couple minutes. So let's go back to our foliate. It's this guy. All right, we need to find the derivative, and this one we have to do implicitly. Like there's no other way because we can't get y equals something here. Like it's not possible because this is a few different functions all combined together. So what we do, we just start from the beginning. So we have x cubed, so something cubed. The derivative of something cubed is 3 times something squared times the derivative of that something, so the dx, plus y cubed. Well, again, that's going to be 3y squared times the derivative of that something, minus 9xy. Well, xy, oh geez, we're multiplying there. Oh, that means we have to use product rule. So let u equal x, v equal y, du is dx, dv is dy. When you have just xy, you probably won't have to actually show this very many times because, I mean, it's u is x, du is dx, v is y, v is dy. It's kind of redundant, but we multiply just like that. So we have y dx plus x dy, and then it equals 0 because derivative is 0, 0. We're going to need to distribute this -9, so we're going to have 3x squared dx plus 3y squared dy minus 9y dx minus 9x dy equals 0. Now everything has either a dx or a dy. Nothing has both, and there's nothing with nothing. Because if it didn't have a variable, it would have been a 0 because it would have been a constant. So everything has either a dx or a dy. We're going to move all the dx's to one side of the equation, all the dy's to the other. Let's move the dx's across. So we're going to have this dx and this dx to move to the other side, just using addition and subtraction. So that's going to leave us with 3y squared dy minus 9x dy equals -3x squared dx plus 9y dx. Factor out our dx and our dy. 3y squared minus 9x dy equals -3x squared plus 9y dx. And then we're going to divide the dx, and we're going to divide everything other than the dy. So we'll get dy over dx equals -3x squared plus 9y over 3y squared minus 9x. And that is the derivative of this function. You see why we didn't start with this one? Yeah. They get a little bit big. Now, thankfully, we don't have to do much here. We could find the derivative at a certain point, like say at 3, 1. 3, 1 is a point on this graph. We could plug it in. 3 squared is 9 plus 1 minus, I'm sorry, that's cubed. 3 cubed is 27 plus 1 is 28. Yes. Minus 9 times 3 is 27 plus times 1 Maybe that's not it exactly. 3 comma 1. But anyway, if we found a point, we could plug it in. Why did I think that? 28 minus 3 times 27. That would still equal 1. All right, that's weird. I may have graphed it slightly off. May have had a typo there. That's a bummer. Anyway, we'd have to plug in both the x and the y point to find that value. And we'll see that in just a minute anyway. So here's another one. So find the derivative of y squared plus xy plus x squared equals 0. So now there's nothing strange or funny with this. It's done basically the same as the last one, but it's a little bit easier. So this is where you get to try this one. All right, so I'm going to have you pause your video, find this implicitly, then we're going to come back to it. As you can see, there's a little bit of a process here. So this is a chance for you to try it all on your own. So go ahead, pause, and then push play when you're ready to come back. All right, how did you think you did? It's tough. Did you remember to use the product rule with x and y, or with xy? If not, go back and use the product rule with xy. So let's find the derivative here. So the y squared, that's going to be 2y dy plus the xy, well, that's u equals x, y equals v. So we're going to get a x dy plus y dx plus x squared. It's going to be 2x dx equals 0. All the dy's to one side, all the dx's to the other. Looks like these are my dx's. So we're going to have 2y dy plus x dy equals negative y dx minus 2x dx. We can factor out a dy to get 2y plus x dy equals, factor out a dx, negative y minus 2x dx. Divide and divide, so we get dy over dx equals negative y minus 2x over 2y plus x. And that's the derivative of this y squared plus xy plus x squared equals 0 graph. How did you do? If you made a mistake, do you see where you made your mistake? All right, now the second derivative. So for the second derivative, the first thing we're going to have to do is we have to find the first derivative. So we have another equation here. If you wanted to, you could pause this to find the first derivative to check to see if you're doing it right. So, but we have 2x cubed minus 3y squared equals 8. So first derivative, we're going to get the 2x cubed, so the 3 multiplies, so it'll be 6x squared dx minus 3y squared will be 6y dy equals 0 because 8 is a constant. We can move the dx's over. So we have negative 6y dy equals negative 6x squared dx. There's nothing to factor, so we can divide and divide. So we get dy over dx equals, we have 6x, negative 6x squared over negative 6y. The negative 6's can cancel, so the derivative equals just x squared over y. So now we can find the second derivative. So the second derivative, I'm going to move over here, d squared y over dx squared. We're going to take the derivative of what we have, the x squared over y. X squared over y, that's product or quotient rule. So we'll have u equal x squared, v equal y. So du equals 2x, dv equals the derivative of y. I'm going to make that y prime. So for the second derivative, I've switched to just with the y's, you get the y prime. Everything's on one side of the equation already because we have the derivative equals. Notation-wise, for a second derivative, it's much easier to do it where y just gets the derivative of y. And I used y prime instead of dy over dx just to simplify what it is that we're writing. So we have quotient rule. We're going to have this times this minus this times this. So we have 2xy minus x squared times y prime over the denominator squared, so y squared. Now, this is almost in terms of x and y. The only thing stopping that is this y prime. Well, remember, that's the derivative of y. That is this. So we're going to plug that back into this equation. d2y over dx squared equals 2xy minus x squared times x squared over y squared. We can simplify a little bit, like we could multiply those guys. So we have d squared y over dx squared equals 2xy minus x to the fourth over y squared. I mean, there's things that could be done from there. I don't know how much of it actually is simplified and how much of it's adding stuff to other stuff, and it can get a little bit confusing. But this would be the second derivative of this function that we had to find implicitly. Now, if you had to do the third derivative, which doesn't happen very often, usually we'd stop at second derivative here. I mean, yes, it is possible. You would do the same thing. You would find the derivative and you'd have your x's and your y's. You'd end up with y primes in there. So you would just have to plug in y primes. It's possible that you could end up with a y double prime somewhere if you had to do a derivative of a derivative. But you'd have these previous derivatives that you would just have to plug into the equation, just like we did with the y prime in this case. So for second derivatives, a lot of times you have to plug the derivative right back into the equation. I say a lot of times, like pretty much every time, because chances are with your implicit differentiation, you're going to have both x and y, or possibly even just y. As long as you have a y in the equation still, you're going to have to plug in that first derivative. All right, so tangents and normal lines. So if we have this x squared minus xy plus y squared equals 7, this is called a lens a lot of times. It's a ellipse. It's tipped on an axis, so it's not just the normal one. We're going to find tangent lines and normal lines to a point. We're going to use the point -1, 2. It's this point right there. And we can plug this in and find that, hey, if we plug that in, that does equal 7. This one is actually on the graph like we thought it was. So the very first thing we have to do is we have to find the derivative, because for a tangent line or a normal line, we need a slope and a point. We have the point. The point is -1, 2. We just need the slope, and that'll give us a tangent, and from that we can also get the normal line slope. So the derivative, you could take this chance to pause this, see if you can find the derivative on your own. All right, then come back. We're going to go x squared. That's 2x dx minus the xy is going to be, we have minus x dy and minus y dx. That negative got distributed to both of these, plus 2y dy equals 0. So the dx's are going to go to the other side. So that leaves us with some dy's. That leaves us with a negative x dy plus 2y dy equals, and then we'll have a y dx minus 2x dx. We can factor out the dy. I'm also going to switch, instead of negative x plus 2y, I'm going to write 2y minus x dy equals y minus 2x dx. Divide and divide, so we get dy over dx equals y minus 2x over 2y minus x. So that's the equation for the derivative, the equation for the slope. We want it at the point negative 1 comma 2. So let's plug that in. Negative 1 comma 2. So we're going to have 2 minus 2 times negative 1 over 2 times y is 2 minus negative 1. So that's going to be 2 plus 2 is 4 over 4 plus 1 is 5. So our slope of the tangent line is 4/5. So y minus the y part of our point equals 4/5 times x minus the x part of our point. That's in point slope form. We can distribute and then we can add that 2 over. So y equals 4/5 x, and then plus 2, that'll be plus 2 and 4/5 or 14/5. So if we were graphing this one, so 2 and 4/5, 2 and, that's pretty close to there. Nope. And then, yeah, it looks like it might be a tangent line right there. And then for the normal line, normal, a L doesn't have a cross on it like a T does. English. So a normal line, our slope, instead of 4/5, will be negative 5/4. Use the same point. Y minus 2 equals negative 5/4 times x plus 1. Distribute. That's 5/4. Add the 2. Negative 5/4 x, and let's see. Negative 5/4 plus 8/4 is going to be plus 3/4. So we have 3/4. We have that point. I mean, we can use a slope, negative 5/4 as well, and cross, and 90-degree angle right there. So that was finding the tangent curve and normal curve. We've been doing that for like a whole chapter now, but every once in a while, seeing an example on how to do it is not necessarily a bad thing. So again, you find the derivative, plug in the point, not just the x value, the point, because it is a slope at that point on the curve or on the surface, sometimes it'll say. Rational powers. So rational powers would be like x to the 1/2. That's the square root of x. How do we find the derivative of those? Well, we know we have the power rule, and we know that the power rule works for positive and negative integers. Well, it also works for any other numerical power, rational powers, even irrational powers. We don't get that all that often, but it would work for an irrational power as well. As long as it's like x to a number, it works. And if it's like here, it says u to a number, well, that takes into the account the chain rule, because we would have it equals n times u to the n minus 1 times du. So How would these work? So let's say that y equals the square root of x. Well, square root of x is just x to the 1/2. Means y prime will be 1/2 times x to the negative 1/2. We could rewrite this using a root if we wanted to. The negative puts it to the bottom of the fraction bar, and the 1/2 gives us another root. So this could be rewritten as 1/2 root x. We could have y equals x to the 9/8. So y prime would be 9/8 x. When we subtract 1, that takes us down to 1/8, because we'd have to subtract 8/8. You still have to use fraction addition appropriately. So we get something like that. One of the ones that people struggle with a lot is y equals x to the 2/3. Because they'll say like, so y prime equals 2/3 x, and they want to say to the 1/3 because the whole subtracting 1. Well, when you subtract 1, you're subtracting 3/3. So that actually makes x the negative 1/3 on that. And this is true, this works with chain rule, product rule, everything else. So if we have y equals the square root of x cubed plus 2x, we could rewrite this as y equals x cubed plus 2x to the 1/2, which y prime. So we're going to have 1/2 times that something, x cubed plus 2x. That doesn't change. Then subtract 1, so negative 1/2, times the derivative of the inside, 3x squared plus 2. We could rewrite this if we wanted to get y prime equals, so this piece is still on top. So we have 3x squared plus 2 over this 2 times the square root of x cubed plus 2x. So it could get rewritten to be like that. Rewriting it is nice when we have to plug in a number, because when you have something to the negative 1/2, it's hard to think of what that actually means. But if you rewrite it with a square root in the denominator, it's usually a bit easier to figure that out. So the rational powers, you use the power rule just like anything else. Chain rule may be used along with it. It can be used in conjunction with the product and quotient rule and everything else. Like, it all works together. So this just expands on the things you can take a derivative of with exponents. So I will see you in class when we will be working on this more. Until then, keep working problems, keep asking questions, and as always, happy mathing.